As we continue to discuss quadratics, our next topic will be systems of quadratic equations. So we must first review how to solve a system of equations from Algebra 1. So in Algebra 1, you were given a set of two linear equations, and we could solve this system either graphically or algebraically. If I wanted to solve this graphically, I have here two lines, y equals negative 3x plus 1, which I can graph over here. The y-intercept is at 1. My slope is negative 3, which means I go down 3 and right 1, and down 3 and right 1. But I can also go up 3 and left 1. And once I have those points as best I can, I put a line through them. Now I have the second line here, which is not in slope-intercept form. So if I put it in slope-intercept form, that would help me. So if I do this, I can subtract 3x. I can divide by negative 2. And I will get that y is equal to 3/2 x minus 8. So I'll go down to negative 8 on the y-axis, which is down here. Slope of 3/2 means I rise 3 as I go over 2, which will put me right here. And I'll plot another point just to get a better look at the line. So my graph looks something like this. So I've graphed the system of equations. The solutions, you might recall, are the points of intersection. So whether we're doing this algebraically, whether we're doing it graphically, the solutions of a system of equation represent the points where the two curves would intersect. So in this case, the solutions, or the single solution, is the point 2, negative 5. But it is an ordered pair, the ordered pair where these two lines intersect. Now most of the systems that we'll be dealing with, we will have solutions like this. We will have one or two solutions. But you might recall, just to remind ourselves, when we did this in Algebra 1, you would have the possibility of a system with no solutions. That being right here, if I had something like y equals 2x plus 2, that might be something like this. Y equals 2x minus 3, that might be something more like this. These lines are parallel because they have the same slope. And there's also the possibility, this will not come up this year, that you had infinitely many solutions. And that is the situation where you have really the same line. So right here, if I imagine moving this around a little bit, the opposite of y is equal to negative 3x plus 1 dividing by negative 1 gives me y equals 3x minus 1. So I have an infinite number of solutions because these are the same line. So hopefully those sound familiar from Algebra 1. We will not really run into those situations when we're dealing with quadratic systems. I'm mainly going to review how to solve linear systems today, but just to look ahead a little bit. When we're looking at quadratic functions, systems involving quadratic functions, that being either two parabolas or a parabola and a line, our problems will have either 0, 1, or 2 solutions. So if I wanted two solutions, I can just imagine a parabola or a line that intersects this curve twice. And I could see here I would have two solutions. If I wanted one solution, this is a little bit harder to visualize, but you can imagine either a line or another parabola which very, very carefully intersects this parabola right here at a single point. We would say these curves are tangent, intersects at a single point. And if I want no solution, then that would mean I would want either a line or parabola that just misses this parabola entirely. Now it could be that I have a parabola sitting inside here, or I have that line or parabola just completely outside the first one. This will be mainly what we were looking at this year, but again, that's looking ahead a little bit. So we just looked at how to solve this graphically. Graphically, we know the solutions to a system of equation are the points of intersection, which there can be one, there could be none. When we get to quadratic systems, there could be two. How do I solve these things algebraically? Well, there are two methods for solving a system of equations algebraically. The first method, and the one that we will be using mostly this year, is solving by substitution. To solve by substitution, what you're going to do is take one of these equations. You can solve it for either x or y. I will then substitute into the second equation, whichever one I didn't solve, and find the value of the other variable. Now, once I know the value of that other variable, whether it's x or y, I can go back and find the value of the first variable I solved for. That sounds a little confusing just hearing it out loud. Let's see how this works out in practice. This first equation right here, x minus 2y equals 13. I can solve that for x very easily. X is equal to 2y plus 13. So now comes step 2, the actual substitution. In the second equation, negative 3y is equal to 2 times x minus 5. Well, x is 2y plus 13. If I distribute here, I get 4y plus 26 minus 5. So negative 3y is equal to 4y plus 21. Subtracting, I get negative 7y is equal to 21, which makes y equal to negative 3. So all of that is step 2. This was step 1. Here's step 2. Once I know that y is negative 3, I can then circle back to this equation. X equals 2y plus 13. What is y? Well, y is negative 3. So I get x equals 7, y equals negative 3. This means that if I were to graph these two lines, they would intersect at the point 7, negative 3. Because, of course, I list the x coordinate first. Algebraically, this also means that the point 7, negative 3 would satisfy both of these equations. So if I put in 7, negative 3, I would find that it makes this first equation true, it makes the second equation true as well. This will be the primary way that we deal with solving quadratic equations, but there's a very good method that works for linear systems as well, which we should review. Now, even though this works very well for linear systems, it doesn't actually work very well. It's not really useful for quadratic systems most of the time, which is to say you'll pretty much be using substitution when it comes to quadratic systems. So elimination involves eliminating one of the variables. In order to do this, you would end up multiplying one equation, or both, by a constant so that you can eliminate a variable. I will then add my new equations together, actually doing the elimination and then solving. Once I have that value, I can substitute back to find the other variable. Let's take a look. So I see here I have 3x plus 2y equals negative 10. I have negative 2x plus y equals 9. Notice that everything is aligned well. Well, I see 2y and I see plus y. So if I take this second equation and I multiply by negative 2, I will have 3x plus 2y equals negative 10 and 4x minus 2y equals negative 18. So I can then add these two equations and get 7x plus 2y minus 2y is 0. That's the idea. That's the elimination. I have eliminated the variable. 7x equals negative 28, which means that x equals negative 4. If I know that x equals negative 4, I can now go to either of these two original equations to find x. Doesn't matter which one. You might notice that one of them might be easier. But either way, you should be able to get the correct answer. If I went to the first equation, I have negative 12 plus 2y equals negative 10. If I add 12 to both sides, 2y equals 2 and y is equal to 1. So finally I write my solution as an ordered pair, negative 4, 1. Alright, let's take one more look at that. Let's do one more example. In the next example right here, I see 2x plus 3y is equal to 19, and 3x minus 5y is equal to 0. Again, everything is aligned, and I want to multiply one or both equations so that I can eliminate either x or y. It doesn't matter which one I choose. Well, it's not as simple as the previous problem where I could just multiply by negative 2 and I would be able to eliminate the y's. I have 2x and 3x, I have 3y and minus 5y. Here you must multiply both equations by some constant. I will multiply the first equation by negative 3 and the second equation by 2. Why? Well, this would give me negative 6x and 6x. And I'm multiplying the whole equation, so I would have negative 3 times 3y, and negative 3 times 19 is negative 57. Down here I would have 6x minus 10y is equal to 0. Adding these, I eliminate the x's. This is 0. Minus 19y is equal to negative 57, which means that y is equal to 3. Knowing that y is equal to 3, I can go to, again, either of these equations to solve for x. Doesn't matter which one. I'll go to the second equation because I think it's going to be a little bit easier. 3x minus 5 times 3 is equal to 0. That's 15. So this will mean that 3x is equal to 15, which means x is 5. So my solution is 5, 3. This is algebra, so of course I can check my answer. If I put 5, 3 into each of these equations, I will see that it does work, and that is the solution of this system.